I am blue. She's everywhere. All right, guys, so anybody have questions from homework, from quiz?
I had a question.
Yes.
So for the last question on the quiz, how are we supposed to find B, like without it being there? Like how are we supposed to find it with the other equations?
What information did I give you?
A and I forgot the given one as well.
Yep, and the or. Right? I told you the value for A or B, right? Probability. And isn't there a formula that goes with probability of A or B? Right?
Yeah, A plus B minus A and B.
Yeah, basically, yeah, I like it. And don't you know all of those things at that point except for probability of B?
Yeah.
So then you can do like algebra stuff. You can throw all the other values in and solve for the one you don't know. I had a lot of creative answers on that one. People kind of creating formulas. But it's always, you either write a formula for what it is that I asked you, or you write a formula for something that I gave you. There is no formula for probability of B, right? There is no formula for that. But there is a formula for probability of A or B, and I gave you that value. Does that make sense?
Yeah, thank you.
Sure. But I mean, a lot of people had trouble with that one. So not like a lot of people, but a decent number. So it wasn't just you. How's everybody else? You guys all right? Yeah?
Yes.
Of course, nowadays it's a relative answer to that, right? I am 2020 okay. I think it's going to be the thing. So once we're out of the pandemic, if you want to say you're not doing too good, you'll say I'm 2020 okay, which means things are shitty. So on that bright note, if there's no questions from the quiz or from homework, I'm just going to launch right back into where we left off. So make sure that is true. Does anyone have questions before I launch into more stuff? Questions from the quiz or from homework? Or general? We're in somebody's kitchen. That's neat. I like it. It's kind of awesome. Okay, all right. So let's do this. Let's kind of remember what the hell we've done so far. So we're in binomial probabilities. I desperately need you guys to get into chapter 4. If you're working on chapter 3 homework right now, stop. Work on chapter 4 homework, right? We already had the chapter 3 quiz. Do you still have to do chapter 3 homework? Yes. Will I still accept it? Hell yes. Right? You can turn in chapter 1 homework on the day of the final. Will it be late? Oh yeah, just a bit, but I'll still give you something for turning it in. Everybody with me? So your concern is always related to the next assessment that's going to happen. So if you are in chapter 3 right now, stop working on that. Work on chapter 4. You want to be current with what we're talking about. Okay. So I'm going to get back into section 4.3. Unless anybody who just logged in has a question from 4.4. Let me spotlight myself because I want all the attention on me. All right. There's a good chance that the lecture is going to be interrupted because I have somebody has given me a broad time to come take a look at something in the house, which is great. So they can come in anytime. That's awesome. So what let's kind of build back up to where we got last time. Yeah, there you go. So we were doing a problem. Let's kind of catch back up with where we were. So if I have, for example, the probability that somebody likes lima beans, let's say is 35.2%. I love it. And I want to know if I pick 53 random people, what's the probability that exactly, let's say, what do you got, Jeff? I don't know, Jeff. Shit, why did I have to do that? 1/3, let's say 18. Let's see how that goes. I want to make it come out something not too freaky yet. Sorry, I got to check something. Make sure your names are your names. You know what I mean? There's a few in there that I don't think I have some of these people in my class. Change your name to your name. Okay, is everybody with me so far? Does it sound familiar?
Is
What
it
we're doing?
exactly 18 that like lima beans, or is
Oh,
it
yeah.
18?
Thank you, sorry. That is important for you to know. I knew it, but I need to tell you that. And that, why is that important? Because now that tells me what the success is, right? I'm looking for somebody that likes lima beans. So what are the variables we're using for this kind of problem? What kind of problem is this? What's the name of this kind of problem? Don't say probability. You gotta be more specific.
Binomial.
Binomial, cool, because there's two things. Either you like them or you don't. I like it. Okay. So I've got N, P, Q that I need to know. What's N? N kicks so much ass. It's always the same thing. What's N here?
Sample size.
And what is it here?
53.
53. I love it. And what's P?
Is it
Point
success?
352.
Yes, it's the probability. So P is the probability of success. And Q is the probability of failure. Right? So why is a lima bean liker a success? Because that just happens to be what I'm looking for. Okay, I like it. And so what's Q gonna be?
0.648.
Yeah. How do you do that? Because P and Q always have to add to be
1.
1. Good. Because they're opposites of each other. All right, so how do I set this up? So the last thing we did last time, I'm pretty sure, is we looked at this NCR on the calculator. So remember, the idea we got to was it's going to be how long the list is times P to something times Q to the rest. I'm going to improve that formula in a minute, but I just want to kind of keep it a little vague as far as what we did last time. So in the calculator, I don't want to make this damn list. Do you understand what it would take to make this list? I'd have to have, maybe it's the first 18 that are P's and the last, whatever the shit, 35 are Q's. Or maybe it's the middle 18 and then the outer ones are Q's. And oh my God, that list is going to be stupid big. Yes, yes, maybe? Okay, so I don't want to do that shit. Thank God I got this calculator that only costs $100. So it better be able to count, damn little thing. So the way that looks, so this is going to be the length of the list is the idea. And the way it looks in the calculator is going to be 53, choose 18. That's going to represent how large the list is. So that's, I think that's the last thing we did last time is we did a few of these on the calculator. So remember that very first example we did with the left-handed people? I didn't need to do this because I could actually make the list. It only had 5 things in it. So that was a list I could handle. This is going to probably have thousands, tens of thousands, possibly millions of entries. They don't have as much space or time. So how many successes do I have then? How many of these do I have?
18.
18. And then how many failures do I have? If there's 18 successes, there's 53 people, how many are failures?
35.
35, take a guess. All right, let me stop for a minute. I really want you guys to see. I haven't written the formula yet, the official formula. I'm about to. But this is, if I have 53 people, how many ways can I choose 18? That's going to be how long the list is. Times 18 successes, because that's what I want, and the rest are failures. So I'm gonna plug that in the calculator in just a second. I'm gonna share my calculator with you guys, but I wanna write below this, I wanna write what the actual formula is. And what was 53? It was N. What's 18? 18 is my variable. What could I have put there? What numbers would make sense here? How many could like lima beans? Anywhere from, I got 53 people. How many could like lima beans? We got 53 people. How many of them? All of them could?
0.
All the way down to 0. So anywhere from 0 to 53. So this is the variable. I just picked 18. So this is going to be N choose X. That's the number of successes. P to the X, this many successes. And this is where it gets a little weird. And you're like, I can sense it. You're all like, dude, it got weird already. But this is where it gets a little weird. How many are left? I have N total. Just like there are 53 total. And 18 of them were successes, so I subtracted to get how many were left to be failures. So how many are left here? If there were N total and X of them are successes, how many are left?
N minus X.
Yes, cool. So the formula makes it look a little worse than it really is. That is easy to get. It's just the rest, but in the formula it looks a little bit funkier. Don't worry, we'll do another problem after this, but I want to show you what this looks like in the calculator. Let's see, has everybody got that? Anybody still writing stuff down?
I am. Sorry.
Oh, I see. All right. We'll do another example. Let me show you real quick what this looks like in the calculator, and then we'll do another example. Calculator, where? There. And here it comes. All right. Oh, Nita. I forgot I had this up here. I want to show you something. I was playing with the calculator yesterday. Look at that neat graph you can make. All right, so I gotta look here for myself. So here's how this is gonna look. 53. Who remembers where the choose is? Anybody?
Go to math. Scroll over to probability. And then it should be NCR.
Yep. So that means so many choose so many. So choose, number 3, 53 choose 18. And just to remind you guys, I think this has happened to us once before. Do you see how it's got the little over arrow? You got to hit over so you come back up out of that subscript. Times 0.352. Let's see if I can get a bird out there. There we go. Sorry, 352 to the 18. Hit the over arrow to come down. Is everybody with me? If you have an older calculator, it might not need you to do that. It might not look the same as this. The newer ones actually have subscripts and exponents. So times 0.648 to the 35. So I get that. How's everybody doing? Oh, sorry, Sophia. Do you have a question? Oh, your hand's
No.
up for some reason. You're gonna
No.
lower your hand. I have power.
Sorry.
That's all right. All right, so no questions on that. Let's
Can you
try
show?
it.
Can you show how to?
Can you
edit
just,
the-
Wait. Santana, were you asking a question?
Yeah, can you just show how to enter that into the calculator again? Because it's not working for me. I don't know why.
When you do this part, do you have subscripts like this?
What do you mean by that? What?
Does it show up like this, or does it say NCR?
It says NCR.
Oh, okay. So you have, let me see if I can switch. Where was this? Yeah, there we go. So let me switch it so it looks more like what yours looks like probably. So if I do 53 probability NCR, so it looks like this, right?
Yes.
And then you put 18. So 53, choose 18 times point, I forgot what it was, 352 to the 18. Is that what it looks like when you keep going like that?
Yes.
Okay. Times 0.648 to the 35. So that's what it should look like all the way across, right?
Yes.
So this, I don't know if anybody else has the same calculator.
It gives me an error though.
Oh. I'm wondering, what is it? You make really sure that it's exactly this. Is it exactly this? Did you leave out at times? Did you put more shit here? When you get the error message, does it say go to? Does it give you a go to option?
Yeah.
Oh, good. Well, always choose that because it'll put the cursor on the problem.
It goes to the 18th power for the 0.352.
Okay. Does yours,
So
does it
what
look
does that
like
mean?
this? Huh?
What does that mean then?
I don't know. Does it not look like this?
I mean, it looks like that, yes, but it's giving me an error.
All right. Can you turn on your camera and put your calculator up real quick? Where are you?
Yeah.
All right. Let me hold on. Let me pin you here. Oh shit. I don't want to do it. Hold on. Keep it right there. Where are you? There you are. Why is Janik over there? All right, hold on. Oh, so yours doesn't look exactly like mine. So I think it looks like you might have not come down from the 18.
It shows a space in between. I don't.
All right, so this is I'm gonna have to work more with
I
you
can stay
directly
after
because I.
class.
What's that? What's that?
I'll stay after class.
Okay. Sorry, man. I was hoping it would be something really obvious, but it is not something obvious. I have a feeling that too much is up in the exponent or something. Like the times is up in the exponent or something. Okay, so let's try another problem. Yeah, exactly. So this, what did we get? Point. Yeah, about 11.3% chance that for any group of 53 people, I'll get exactly 18 that like lima beans. Okay, here, you come back. So 53 choose 18. Let's just do that piece. If I just do 53 choose 18, watch this giant number. I mean, holy shit. That's actually 64, I think that's 64 trillion, right? Thousand, million, billion, trillion, yeah, holy shit. That means that the list I would make, if I listed every single way, and I know I'm a tiny little box, I'm sorry, every single way to have 18 P's and 35 Q's in all the different orderings, is everybody with me? Because in order to do this problem, you have to consider all the ways that you can get exactly 18. Because how do you figure out the probability of something? You do everything that matches what you're looking for. Oh shit. So how many ways is there to take 18 out of 53? Well, there's 64 trillion. That is how long that list would be. Holy shit. So when I do this, look at this piece. What happens to a number less than 1 when you multiply it by itself? Yeah, Alexis, this is true. Does this make sense when I'm asking? What's a half times a half? Somebody says 1, I'm gonna cry. What's a half times a half?
0.25.
Good old calculator. A fourth, right? Which is 0.25. And then a half times a fourth is 1/8. And then a half times an eighth is 1/16. So when you multiply something less than 1 by itself, it gets smaller, smaller. Look how small this is gonna get. So if I do either one of those by themselves, 0.352 to the 18, look how small it is. It's times 10 to the -9. So move the decimal back 9 places. So I kind of want this to make sense on another level. Big is all shit, small as anything. When you multiply them, it comes out to be normal. Yes, maybe. Is that something you really needed to know? No, but it's kind of neat. This is always going to be huge, and this is always going to be tiny. So when you multiply them, you get something between 0 and 1. That's kind of nifty. Let's do another problem that's got less going on, so we can kind of put our hands more into it, right? Let me stop sharing. So let's do a smaller problem like we did last time. I'm going to do a smaller problem, but a little more interesting. So this time, let's have 4 people. Let's have the probability of success be, 0.25, failures 0.75. So what's the probability that, I'm curious, well, we'll see. I don't know how it's going to come up. Exactly 2 successes, right? So I'm just getting right to the chase here. I'm not even figuring out what physically this means. I'm just going to look at the math of this. Can we make this list? Yes. So I got 4 people. I want exactly 2 successes. So what's the easiest way to make a list of 4 people with exactly 2 P's?
Make them the
I'll-
first 2.
Yeah. So PP, QQ. Right? So this is going to be a little more interesting. Let's see if we can get everything. So let me do everything that's got a P first. So I'm going to let this guy float through. Does that make sense? Let me stop for a minute. I'm not done yet, right? But how's that so far? Yeah, yeah. So you want to attack this very strategically. So now let's do everything that where P is second. Right, so P's got to be second now. Is that cool? And then we'll do all of them where the P, there's a P third, and that's basically the only way to do that. So you can see, I mean, the minute these numbers get a little bigger, this gets harder to create because you have to do it a very systematic way because you could very easily forget somebody. So thank God we don't spend a lot of time learning how to make these kind of lists. All right, maybe. Does anyone see any that I missed? I don't think so. So let's check it out. What can I check in the calculator right now to make sure I did right? How big is my list apparently?
6.
6. So what should equal 6 if I do it in the calculator?
Four, choose
So how
2.
many? Yeah. I've got 4 spots. Choose 2 of them. So go ahead and try that out. Do 4, choose 2. And let's see if we forgot any. What are you guys getting?
6.
I got 6.
6, yeah. So do you see the connection now? I know it's really easy to lose the connection when you start just putting shit in the choose, like the 53 choose 18. But it is always how long this list would be. And this list represents all the ways to do this, which is what probability needs. It needs to know all the ways to do what it wants. That's what probability is built off of. And each of these mathematically, so I could do it this way, success first and a success second and the failure third and the failure fourth. Or I could do it or sound like a seal. And so math is kind of laughing at me, right? Like it always does. Come on, math. How would I write? Every single one of these is the same stupid thing. Every single one of these comes out to be what? How can I rewrite every single one of these? What is
P
P
squared times Q squared?
Yeah. And how many of them are there when I add them all up? So this is always, this is always what is physically happening when I use the full formula. It's just the minute I make these get bigger, I can't really make the list easily. So this in the calculator will always tell me how big the list would be. And why do these exponents make sense? I want exactly 2 successes, which means I would get how many failures? 2, because I got 4 people.
How do we know when the sample size is too big to write it out?
Oh, you are never gonna have to do this. You with me? There might
Okay,
be
got it.
problem 3 that you got to do something, but I mean that's the most. It doesn't take much to make this become really, really difficult. And you just have to be very organized. So the minute this is 5, do 5, choose 2 real quick. What's 5, choose 2?
10.
10. So we're starting to get kind of big. So if I did, now do 6, choose 3.
20.
Yeah, so can you imagine? I want you to really imagine. All it took was to have 6 people with 3 successes, and already my list is 20, which makes it really easy to miss 1 or 2 or 3 unless you're very organized. So that's not the point of this class. We're not gonna, it's not a list making class. Thank the gods, right? Okay, I don't think we offer that here. So to do this problem, let's put everything together. It'll be 6 times p 0.25 squared times 0.75 cubed squared. So that I can just throw in the old calculator. Let's see, what's that gonna be? 1/16, 9/16, 9, 27, 16. I don't know. Shit. Did I do that in my head? Am I? I'm gonna try. I lost it. Screw it. I think I'm not, I don't remember where I am. What do you guys get when you do that?
.2109.
Yeah, I like it. So 21% chance that from any group of 4 people we'll get exactly 2 successes when the success rate is 20. So, I mean, let me see if I could say this from a purely mathematical standpoint. So if there's a probability that somebody has coronavirus, and I don't know, you take like some large gathering of people, maybe at an airport or something, and you think about what's the probability out of all those people that there's at least so many that are infected. Well, that's going to be more than 0. And then, of course, they're near other people. So what's the probability other people will be infected? Anyway, you guys kind of follow what I'm saying? That would be based on this idea, but it gets a lot more complicated, obviously. But it's still the same idea. All right, okay. So neat. So once again, here's the formula. So when we put it together, it was 4 choose 2, 0.25 squared, 0.75 to the 4 minus 2. And of course, this, we saw 2 different ways that it's 6. Yeah, from 2109, I like it. All right. Let me give you guys one to try on your own. Keep the formula up there. So let's say that, what do you got, Jeff? 87% people want the election to be over. We randomly pick 42 people. What's the probability that exactly become a team? Let's see, what's going to make sense here? 35 of them want it to be over. So we catch up to you guys a little bit. What's n?
42.
Somebody else tell me what p is.
0.87.
0.87.
Now somebody else tell me what q is.
0.13.
And then somebody else tell me what x is. Aw, I heard a little one out there. 35. Right, successes. How many successes? I want 35 successes.
Where
now-
did you get point 13 from?
If the probability of succeeding is 87% chance, what's the probability of failing?
Okay, thank you.
You're welcome. So all p and q must always add to be 1 because they're opposites of each other. So now I just got to plug and shove. 42 people choose 35 to be a success. So how many successes do I want? Well, I want 35. I just said that. Okay. So I like that it's a little repetitive. Choose 35 successes out of 42. Well, how many successes? I want 35 successes. How many failures?
Power of 7.
Yes. So the overall, you still have 42 people. I love it. So you can always do a quick check. These better add to be 42, or else you lost somebody, or you created people, which is always neat. Let's see if I made one that comes out nice. Yeah, cool. I like it. Let's see, I got somebody, I think you're suggesting, yes, you're almost right, person. Oh, you didn't do private, so you are right, almost. There you go. One little thing you just have to round. So it should be 0.12, what was it? 94. The rounding is not that big of a deal. How we doing out there? You guys all right? So,
All right.
yeah. Because I really want you guys to realize that they set themselves up. 42 people, choose 35 of them to succeed. So I got 35 of these and I got 7 of those. It really does set itself up if you let it. I'm going to ask a different question about this. Has everybody got this? Okay. What's the probability that at most 41 wanted to be open? Oh shit. We haven't done a problem like this yet. What's at most 41 mean?
41 or less?
Yeah, which sucks. Because what's 40? So I'd have to do the probability of 0. I do that entire formula with 0 successes. Plus the probability of 1. I do that entire formula with 1 success. Plus all the way up to 40 freaking 1. You guys understand? Do you want to do that? Good. If you did, you're just weird, but that's all right. I'd much rather do the opposite. What's the opposite of this? What's the only thing that this leaves out?
42.
42. So if I do 1 minus the probability of 42 successes. So if I do this with the formula, and whatever I get, I do 1 minus that. That little 1 minus trick is freaking cool as shit. I'm gonna always do this if there's way too much work over here. I can always do 1 minus whatever this leaves out. And just to really like hammer this home, isn't if I did this, what do I get? If I add up all the probabilities, what do I get? If I add up
1.
yeah, I gotta get 1. So then if I do this, doesn't that become the question, right? I mean, that's all I'm doing. That's all I'm doing. 1 minus what this leaves out equals all this shit. Because all together they make 1. So now you can just focus on what's the probability of x equals 42. So go ahead and do that. Set up the formula. When you get that, you do 1 minus that. It is probably going to be freaky. I don't know. Let's see if it's freaky. Maybe it's not going to be freaky. No, it's not freaky. Yay. So it's going to be, you do it down here. Right, that's what it's going to look like when you set it up. 42 successes, which means no failures. So what do you guys get? Anybody do that yet?
0.0029.
By the way, what is 0.13 to the 0? What's anything to the 0 power?
1.
Yes. How many ways? If you had 42 people, how many ways could you choose 42 of them?
1.
So isn't that 1 and that's 1? So if I just do that, I'm going to get the same answer. Do you really have to know that? No, but it's something, you know, something to remember. I only have to worry about doing this thing. But, so what's the answer then?
But she can't afford
I got
she can't afford to pay for it
0.9971.
herself.
Yes. Oh, give me 1 second, guys. They're here to do their thing. Hold on. All right. So they're going to work on that. Is everybody cool with that? Uh-oh. It's going to be some drilling. Any questions from there? Okay.
Sorry, just a quick question.
Yes.
When you find N, P, Q, and X, and then you plug it into the equation, are you basically just solving it like PEMDAS?
Oh, all right. Let me make sure I understand what you mean. So that last one was this one. It's already out of my head. There it is. I love your question. We're not doing this by hand, so we don't have to worry about PEMDAS. Graphing calculators know math grammar, which is what PEMDAS is, right? What is it that you're concerned about?
I'm just concerned about making sure that I put it in the calculator the right way so that I get the answer. But is that?
Oh, I see. Yeah, put it all in there at once.
Okay.
Yeah, problems happen when students put bits and pieces in. Yeah. In fact,
Okay.
sometimes
All right. Thank you.
sometimes this piece by itself will be too big for the calculator to even handle. But if you put the whole thing in, tiny times big becomes manageable. So that's why you don't want to do it in parts. I like it.
Got it. Okay. Thank you.
All right, let's see.
I was also wondering, so for the example, when we do like at most, what if it was like the variables like at most 36? Then would we
Oh, yeah.
do 37?
So let's see. So if the question would have been at most 36, you got to be really careful. At most 36, what does that leave out? At most 36 means from what to what?
1 to 36.
0 to 36. I'm with you though.
Yeah, 0 to
So
36.
what does it leave out? What does it leave out?
37 to 42?
Yeah. So it's the idea that there's a place where it doesn't matter which way you do it. Because right now, this is still more work than this would be, right? I would still do this compared to that. This is gonna suck, but this is gonna like really suck. So, but there's a point like maybe around 29 or 27 where it's like, who gives a, either way is gonna suck. Yeah. So I am not one to give you too many of those kind of problems. At most, I would say something like this, in which case you would have to do so you'd have to do a formula for that one. You have to do a formula for that one, add them, and then take it away from one. Is everybody with me?
Got
Yes.
The idea never changes. It's always, if there's too much work to do here and the opposite situation has less work, do that. And then do 1 minus that.
Got it. Thank you.
You're welcome. How's everybody else? Now, let me see if you guys, oh, Santana, you okay?
Yeah, I'm fine.
Okay. Let me see if you guys remember this. This is when I give you a binomial situation. So let's say I've got n is 80, p is 0.2, and q is 0.8. I've given you data, right? I've given you information. Anytime I get data, what two things do I want to be able to calculate about that set of data? Does that make sense? What do we always want to calculate?
Mean.
Good, yeah, mean and
Standard deviation.
standard deviation. Things are happening in my house, sorry. So, now what's funny is, what does this mean, this here?
Probability of success.
Probably success, and so there's a 20% chance of success, right? So if I have, so this is sort of like, if I, like, all right, just to pick on old Laker, somebody called Shaquille O'Neal. So let's say that Shaquille O'Neal makes 20% of his free throws. Will be nice. And he takes, he was also a Celtic too, so, goes both ways. And he makes 20% of all, it's just a known fact. How many would you expect him to make if he takes 80 free throws and he makes 20% of them? How many would you expect him to make?
20? 20?
No.
16.
Yes. How many does he make? Period. 20%. How many, if he takes 80, I would expect him to make 20% of 80.
Oh.
Does that make
Okay.
sense? Did I just say that he's definitely going to make 20% of 80? Oh, you all good? Yeah. Is he always going to make exactly 16? No, right? If you flip a coin 50 times, how many heads do you expect to see?
25.
Around what? Yeah,
25
25.
times.
But it would be almost weird to get exactly 25, wouldn't it?
Yes.
That would be a little weird, isn't it? But it's something close to 25. So I expect him to make something close to 16. Is everybody semi with me? We've done stuff like this before, a percentage, and then I had a total number, and then I multiply them to see what I expect to see. Okay. So the standard deviation, so what did I just say? This is interesting. I expect him to make close to 16. And what is it in standard, well, that's the answer. To measure distance in statistics, of course, is standard deviation, right? How you guys doing out there? All right. So standard. So look what we just did. Let me create the mean formula here. So what we're doing, it's another name for mean is expected value. Become a name. The mean is the expected value if I do something a lot. So if I flip a coin 50 times, but I do that many times, and I average all the heads that I get, I should get about 25. Maybe. All right. So the expected value is going to be, well, what was this? What letter is this? What variable?
P.
N.
N. And what letter is this?
P.
P. All right, so that, all right, now compared to, that's it. For a binomial distribution, the mean is just that little tiny formula. That's the best formula we've had so far, holy shit. Right, because what was the formula, the first formula was that, so I had to add a bunch of shit. The second formula was, the most recent formula was this, where I had to make a long column and shit, right? By the way, real quick, what do the first three letters here look like? What do they look like? That's a what? That looks like a what?
Expected.
Yeah, EXP, right? Yeah. Sorry. It's nothing we did on purpose. It's just kind of neat. I just want to point that out. Mean is expected value. That's another name for the mean is expected value. And the formula freaking tells you the shit. All right. Just coincidentally. So compared to these other mean formulas, that kicks so much ass. There's no columns to create. There's no numbers to add. I just multiply those two things. And here's the standard deviation. All right, this one I can't, this one would take a little bit more math than most of us have to explain. But the standard deviation for a binomial situation is this. So can somebody, so the mean for this problem was 16. Can somebody figure out the standard deviation for me? So it'd be like 3.5. Oh, I'm sorry. Somebody said, can you say that again? I'm not sure. I didn't catch that chat when it came in. I'm not sure what I was saying. I'm very sorry.
I got 3.577.
Yeah, that sounds about right. 7.7?
Yeah.
All right, so now watch. Stay with me. I'm gonna push this a little further. Remember what I just said a minute ago. Does this make sense? If somebody makes 20% of the free throws, I would expect them to make 16 out of 80. And again, that doesn't mean they're going to get exactly 16. They should get close to 16. So what the hell is close to 16? What does that mean? So I can use standard deviations to help me figure that out. So this is related to the idea of unusual. When does something become unusual is when it is beyond 2 standard deviations from the mean. If you are more than twice the average distance from the mean to the data points away from the mean, you are in unusual territory. So if somebody's height was 2 standard deviations below the mean, they are unusually short, officially, right? Or the other way around. If there's 2 standard deviations above or more than that, then they are unusually tall. All right, so here, we'll take some of this excess stuff away. My mean is 16. So what I can do is I can make a little visual for myself. We've done this before. If I go 2 steps up, which will be, let me see if you guys are cool with this. It'll be 16 plus 2 of these, right? Is that cool? If I add the standard deviation twice, so add this twice, where does that get me to?
23.154.
Sounds right. And then if I go 2 steps down,
Just coaching though.
8.846.
like it. So that would be the min and max usual values. So if Shaquille O'Neal took 80 free throws and made, if he made 26 free throws out of 80, would that be unusual officially?
Yes.
Yes.
Because the maximum usual is 23.154. So this kind of describes, this kind of explains what far enough away is. And this is huge. I'm going to spend just another couple minutes on this idea. And I want to do a problem with flipping a coin. I'm going to do that in a minute because we've talked about that before. So anytime I've got a mean and a standard deviation, I can figure out what the min and max usual values are. Anything outside of there would be considered unusual. So if I was in a nuclear power plant and I've got my ass sitting down in front of all the dials, right? And Bryan Cranston's in the background yelling about Godzilla. And I see one of the little meters going towards the red. That is basically saying you are so far away from what's usual that you're more than this much beyond. Does that make sense? I mean, that's how they calibrate what that is. If things are outside of what's usual operation, then that's what's going to make it go yellow and then red. So yellow might be 1 standard deviation away and then red is 2. Is that all right? Does that make sense? Yellow's like, I better go take a look. Red is like, holy shit, it's going to about blow up. We should go take a look. Okay. Maybe. Yeah, okay. So I'm going to do one more example of this stuff. And then well, you guys want to take a break right now?
Yeah.
Like 10-minute break? I'm not going to do too much more after this. Let's do a 10-minute break. So come back. We'll make it 2:43. A little bit after 2:40. Come back. All right, so first thing I want to say, I already changed some of the assignments and the homework, and then Janek reminded me why that was that I did that, because the next quiz is scheduled for Monday, which is now a little insane. So I was going to move that to Wednesday. That'll be a little bit better. So we're about a day behind the quiz schedule, which is fine. So the quiz that was scheduled for Monday will now be a week from today. How you doing out there? All right. So I want to do that example of flipping a coin, and then I want to get into chapter 5 a little bit. So if I flip a coin, let's see, I always forget what number works for this, but oh well, we'll just feel it out. Flip a coin, let's say 400 times. What's the expected number of heads?
Around 200.
Say again, sir?
Around 200.
So if you do this, we're assuming a fair coin, right? Just the normal coin hasn't been messed with. Then I would have n times p, and of course, the probability of getting a head is 50, probably getting a tail is 50% for a nice normal coin. So that would be 200. Now take a minute and figure out the standard deviation. This will be nice. It should come out nice.
I got 10.
10, yeah, because half of 200 is 100, square root of 100 is 10. Yeah, that's beautiful. So I don't know if you guys remember, I'm pretty sure earlier this semester, but it's possible I didn't. If I had a coin and I'm like, I think this coin's been messed with. If I flip it 400 times and I get 198 heads, that's obviously not evidence, because that's not very far away from what I expect, right? So what is far away enough then to be evidence it's been tampered with? Well, now we know. It's that idea of unusual. So where does it start to get unusual? Well, this number kicks ass. What's the upper limit? What's the lower limit?
$190 into 10.
Careful, you go how many steps?
180 and 220.
Yes, you got to go twice, 2 steps. Stop right there for a minute. So officially, if I flipped a coin 400 times and I got 230 heads, is that evidence that it's been tampered with? Yes, it is. Is that proof that it's been tampered with?
No.
Hell no. What if I flip a coin 400 times and I get 400 heads? That is obviously evidence that it's been tampered with. Is it proof that it's been tampered with? No. Is it impossible to get 400 heads in a row with a normal coin? Is that impossible?
No.
No, but humans, I've heard, have a really difficult time about what is unlikely versus what is impossible. We have a very hard time with that, right? When we hear something like there's a 2% chance, we're like, well, it ain't gonna happen to me, and then it happens to you, because 2% doesn't mean it's never gonna happen. You guys semi with me? All right. And real quick, what number of heads should have the highest probability? What number of heads do we expect?
200.
200. So that should have the highest probability. Can you figure out the probability that you get exactly 200 heads out of 400 flips? What does that sound like? Sounds like a math problem, Jeff. Yeah. I got 400 flips. Oh, sure. We can keep this shit up here too. 400 flips. And I want 200 exactly, right? You can set that bad boy up. So it'd be 400 flips, choose 200 of them to be heads. So it'd be 0.5 to the 200, 0.5 to the 200. Right, if I got 200 heads, it means I got 200 tails. We're not counting it if it lands on its side. So let's see, I don't know if that's gonna overflow the calculator. It might. Shit. Yeah. You guys get an overflow error?
I did.
Yeah, sorry. So that's what I was trying to figure. I was trying to remember. I do this and I always forget what's a good number to use here so that it doesn't overflow. It's just the numbers got way too crazy for the calculator even to handle, which is kind of amazing. Anyway, too bad for us. But I wanted to show you, even I'll bet you anything that this probability is less than 5%. Because even though this is the most likely thing to happen, there are so many other things that could happen that you only have like less than 5%. So everything else is going to be less than 200, the probability of 200. But 200 itself is going to be really unlikely because there's so many things that can happen. So that kind of gets confusing because less than 5% is unusual, but it's because this entire area out here has a less than 5% chance of happening. Any individual thing could be the most likely thing, but have less than 5% chance of happening. That's why if I flipped a coin 400 times and got exactly 200 heads, that would still be freaky because the probability of exactly that happening is low, even though it's the most likely thing to happen. What the shit are you talking about, Jeff? I don't know anymore. All right. Oh, that's what Stanford. So I want to do a little preview of chapter 5, and then that'll be it. So all the distributions we've been doing so far, so like a basic probability distribution from section 4.1 and 4.2, where I give you x and p of x, right? This a binomial distribution, where if I have 80 things, then x could be anywhere from 0 up to 80. Is that right? Yeah, it's the shit we just talked about. Are those examples of discrete distributions or continuous distributions? Just to dredge up some old terminology.
Discrete.
Totally, because what would it mean to be continuous? What would need to happen? Why is this discrete? Because what does discrete do? This is 0, 1, 2, right? Because I can't have half a person. And
Okay.
continuous is supposed to be able to take on any value between 2. So obviously a problem where we're talking about number of people or flipping a coin, that's not going to be continuous. I like it. You can't get 60% of a head when you flip a coin. That doesn't make any sense. It's either a head or an ain't head. All right. So what we're about to get into are continuous probability distributions. And the most basic type, we analyze this just to get ready for normal distributions. We're getting into normal distributions very soon, chapter 6. This is chapter 5. This does not happen very often in real life perfectly, but there are a few situations that get close enough. So we're going to analyze this idea just to get ready for normal curves. So, for example, if I had to go to a bus stop, and the bus came every 15 minutes, and let's pretend like we're in Germany, all right? Not in San Diego, where every 15 minutes means, you know, it's not late until it's 28 minutes late. You guys with me? If we're in, has anyone ever been to Germany? I went to Germany, and I mean, if that train was 2 seconds late, it's like, good night. And then I went to Italy, and the train was 2 hours late, and I'm like, what's going on? They're like, that's 2 hours, that's not late. Holy shit. Anyway, so let's pretend like we're in Germany, where that really means what it's supposed to mean. So tell me this, how long, if you get to the bus stop, what is the least amount of time you could wait?
No time.
No time, because maybe the bus came right there as you got there. Bam, you just go right on. You waited 0 minutes. Or what if it's just pulling away right when you come? How long do you have to wait now?
15.
15 minutes. So if you get there and there's no bus there, you have no idea. It could be anywhere from 0 to 15 minutes. Is everybody with me? Does any time, should any time have a higher probability than any other time if you get there and there's no bus?
No.
No, 2 minutes later, 8 minutes later, 15 minutes later, any of them could happen. They're all equally likely. So what this is going to be called is going to be called a uniform distribution. So this is going to look like this. Big box. So it's sort of like a histogram where there's an infinite number of rectangles and they're all the same height because none of them are more likely than the others. How are we doing out there? There are very few situations in the real world that are perfectly uniform, but this gets pretty close. Okay, now stay with me, stay with me. All right, so this represents like a histogram for 0 to 15 minutes. How tall does it have to be? If this represents the probabilities from 0 to 15 minutes, what should the whole area of this be? What should the complete probability be? Say again?
Oh.
So the whole area should be 1. That's related to the probabilities adding to be 1. All right, let me slow down for a second. So a quick side note, quick side example. Does anyone ever throw darts? Anybody ever, even in a bar? I don't mean you have to do it for a competition, but you know darts, you know, throwing darts? And hopefully not too many go in somebody's head. So you got the dartboard. And it very, very, very basically looks like this. Very basically. All right, that's the all-knowing eye. And there's supposed to be 20 of those or whatever. I don't know. I don't really do darts. If I wanted to know the probability, if I just throw it at the board and I don't count it if it misses, if I wanted to know the probability it hits in this triangle, I really want this to make sense. Why is the probability it hits in this triangle more than the probability it hits in the bullseye? Why is that a bigger probability than that?
The area.
The area is more. So if the total area is 1, if I just force it to be 1, then this area would be like point something, point whatever, right? In fact, there's 1, 2, 3, 4, 5, 6, 7. Of course there's 7, Jeff. Why would you do that? Screw it. So let's say that the area of the little circle inside, let's say that it's 0.08. So what's the probability that I just kind of blindly throw a dart and it hits the bullseye? 8% chance. So any situation where I have an image of the probability. So this is a physical image. I can touch the damn thing, but it's a circle. If I make the area 1, the probability of landing anywhere is related to the area of that region. Because that's the percentage of the whole 1 that it is. So this being 1 makes sense. The whole area's got to be 1 because all the probabilities have to make 1. So can somebody tell me how tall the damn thing has to be then? If I know the area has to be 1, and there's how tall would it have to be? What's this length?
15.
So how tall would it have to be to make an area of 1?
1 divided by 15?
Yes, the reciprocal. I like it. MIT. So now watch this. This is the absolute last thing we'll do. Yeah, I'll let us out here a little early. The probability that I have to wait between 2 and 5 minutes, right? The probability I have to wait between 2 and 5 minutes. I've got my distribution. I've got my height. I draw in my 2 to 5. The answer to this question is the area of this rectangle. Because areas relate to probabilities, just like on a dartboard. So what's the area of that rectangle? What's the width?
3.
3. And what's the height?
115.
1/3.
No. 15.
15.
Our world didn't become 2 to 5. It's still 0 to 15. That could still happen. My question is, what's the probability that it'll be 2 to 5? What could it be? 0 to 15. I don't know. So what's probably is 2 to 5 will be the width times the height is 1/15 because it's in the situation. 3/15 is 1/5 is 20% chance. So uniform distributions kick so much ass because their areas are easy. They're just rectangles. When we get to a normal curve, does that look like something your geometry can handle? If I want to know this area right there, does anyone know geometry that deals with a melted side? Do you guys see what I'm saying? Like, what's the area of this thing? Well, what's the melted side angle area formula? You don't know.
Trig?
Not even trig. It would take calculus to do this shit. I'm not going to teach you calculus. Don't worry. As much as I want to, I'm going to not do that. What we're going to do, but what I desperately want you to realize, anytime I have a visualization of the distribution, the area related to a question is the answer to the probability of that. Just like the dartboard, exactly the same thing. So this is a distribution. If I only had a way to figure out this area, I would know the answer to the probability that somebody's between 5 feet and 5'10" or something, whatever this represents. So we're gonna thankfully have a chart that we can just read off of to get the areas. That's some nice calculus people put together. So anyway, I'm not going to talk about calculus. I promise you I wouldn't. All right. If you're me every time, I have no idea what that means. All right, guys, I think that's enough. So I'm going to officially say class is done. If you have any questions, if you want to hang out, let me know.
I just wanted to let you know that I figured out the problem with my calculator.
Oh, good. Thank God. What was it?
Well, I didn't figure it out exactly, but I have to do it in steps. Like I can't do it all at once. You know what I
Oh,
mean?
man.
Like I have
That's
to do
weird.
the NCR and then multiply it by everything else.
That doesn't make
But
any
it
sense,
still
but
comes out
that should
the
work.
same.
That should work for most of our problems. So, you too. Enjoy the weekend. Everybody's all right? I'm going to head out. I don't see any questions. Bye, everybody.
Question.
Oh, yes.
Wait. Okay, for homework, when like when it's asking for more than like a number, you just add up all the numbers. Like if it's asking for more than one, do you add up every number that's more than one, and then that would be like
What are we,
the so
which problem
it
are
was
we looking at?
it was 4.231.
Okay. Oh, yeah. So, all right, let me put this up here. So one of our shortcuts doesn't really help. So let me show you this. This one here, right?
Yeah.
So yeah, so you obviously have to fill this in first, but then well, actually you don't even for this. What's less than 4 up here?
Oh, 3, 2, and 1.
Yeah, so then you just have to add those probabilities together.
Okay. Thank you. Have a nice day.
You too. Let's see, Catherine, Jenna, are you guys out there?
Yeah, I had a quick question. So it's so you know how it's 1/15 for the height?
Yes.
It'll always be like that, like whatever the
Next time I'm going to do a problem. Because I like starting with the bus stop problem, but the problem is it starts at 0. So, so what if it didn't start at 0? What if it started at 2 or something? So what about a problem that went from 2 to 8?
it would be 1/8.
No, because it's not 8 long. How long is it?
Oh, it would be 1/6.
There you go. So that's when I do the bus stop problem, it's a nice one to start with because most of us have been on a bus and we know about waiting for the damn bus and all that stuff.
Mm-hmm.
The problem is it has a 0 there. It makes people think that this number is always, no. It's reciprocal of how long it is. Because now 6 times 1/6 is a total area of 1.
Okay, that was my only question.
Okay, cool.
Okay, thank you. Have a good weekend.
See you. You too.